So, welcome everyone to today's distinguished lecture, part of the series that we have. For your information, everyone here knows we have about maybe 8 or 9 of them per year. It's where we invite the most distinguished people in science related to what we do, and so we're particularly excited today to have Klaus Ensslin, who is a dear friend and former colleague of mine from ETH. Klaus started his undergraduate work actually at the University of Munich, and at the time it was the diploma system, and he did his Vordiplom and then went already to ETH Zurich to finish his studies, and after that he came back to Germany, went to the Max Planck Institute in Stuttgart to do a PhD, and after the PhD he went to Santa Barbara for a postdoc, and after Santa Barbara he came back to Munich to do his habilitation and started his independent research, and basically directly after that he was recruited by ETH Zurich and has been at ETH since 1995, I think. He has done pioneering work in especially on quantum dots, not the optical quantum dots, but the electric quantum dots. And he, I could say, was the big motor behind the whole quantum science and technology initiative in Switzerland. And so we had a lot of fun discussing and at various meetings during my own time in Zurich. And it's a real pleasure to have you today with us in Erlangen. And we're looking forward to see what's happening in the world of graphene these days.
Thank you, Wahid, and welcome to this seminar here. So actually, Wahid and I, we go back many, many years, actually way before either of us was at ETH. I don't know whether you remember that. I had a memorable visit when you were a postdoc in Konstanz. And back then, I think we discussed something on general relativity. That's what I remember. Okay, so thanks for having me here. I realize that graphene is maybe a little bit exotic for this institute here. And so I will give you a very general introduction into graphene and why I think it is interesting. And then I will move on and tell you a little bit about the latest research. So I think this is a question that many people ask themselves, right? Who has the best qubit? And I put down a couple of contenders here, and I appreciate that there are many more around in the world. There are companies working on some of them, research groups, and I want to focus on this one here on the bottom, and I want to go back a little bit in history. So gallium arsenide, as you know, is a fantastic material. It has been around in the semiconductor industry and also in fundamental research. It gave rise to the discovery of the fractional quantum Hall effect and so forth. And it is the material that I think is still the very best that we have today. And the first quantum dots, you see a schematic here, were built this way. So it has a 2D electron gas here at the surface between gallium arsenide and aluminum gallium arsenide. Then you put down a couple of gates on the surface, and that's how you define your quantum dots and your spins and your qubits and so forth. And I think if you want to build, for example, today, 7 quantum dots, each of them containing 3 electrons, gallium arsenide is the way to go. It's the material that works, it's reliable, and it has a lot of fantastic properties, and most of the basic physics, the qubit physics, was actually done in that material. But gallium arsenide comes with some fundamental issues which are related to the material, and one of them is that gallium and arsenic are sort of heavy elements in the periodic table. That means that spin-orbit interaction is relatively strong. And gallium arsenide has very strong isotopes with lots of nuclear spins. And so if you think about spin qubits, that's a bad news because you have all kinds of perturbation around your spin qubits. And that's why this is sort of the pioneer, but we are sure it will never be the material for the future. So then there's silicon. And silicon is a very nice material. Obviously, it's nice because most of our technology is built on silicon these days. And so the idea of upscaling is an obvious idea, right? We know how to build billions of transistors. So then people say, then we also know how to build billions of qubits, which I think is not a good statement. But nevertheless, silicon can be made isotopically pure. You can get rid of all the nuclear spins. And silicon is a relatively light element, which means spin-orbit interactions are weak. And therefore, the spin coherence times in silicon are very good. What I want to convince you is that graphene is the material of the future, because actually if you take natural carbon, it's 99% nuclear spin-free without of you doing anything. On top of that, you know, carbon is element number 6 in the periodic table. There's hardly anything before carbon. There's helium and hydrogen and so forth. There are a lot of useless elements for technology. But then carbon is the first one that is a real solid-state material for carbon nanotubes, buckyballs, graphene, and so forth. And everything that is built from carbon has basically these intrinsic advantages. And that's, of course, nothing new. That has been known for 10, 20, 30 years. But I think we still don't have an experimental confirmation that you can really do something with that in that respect. So here again, 99% of carbon is nuclear spin-free. Carbon is a light element. Very long spin coherence times predicted. None of them measured at this time. So let me start at the very beginning, right? We do solid-state physics 101. This is basically a honeycomb lattice, right? If you take a honeycomb lattice and you position carbon atoms at the edges of the honeycomb, then gives you the graphene lattice. Again, that's nothing new. That's known since the 1950s. And if you build basically the primitive unit cell of the honeycomb lattice, you see that you cannot build it with one atom per unit cell. It's trivial. It's just geometry. You immediately realize that the primitive unit cell has 2 atoms at least. If it were not the honeycomb lattice, but just the hexagonal lattice with an additional atom here in the center, it would be different. Then you could build a unit cell which has 1 atom per unit cell. But for carbon, you need to have 2 atoms per unit cell. That's real space. Now that's K-space, and I'm sure many of you have seen that before. So if you plot energy versus momentum, then you get this fantastic linear relation between energy and momentum. And actually, that's a very old result. That's again from the 1950s. That's from the early days of band structure theory. It was calculated early on because it's an easy problem to solve. And already back then it was recognized it probably will never exist. So it's just an academic exercise to get the band structure right. But the important thing of this band structure here is that you have K and K prime points. So basically these Dirac cones, they occur at inequivalent K and K prime points, and they are directly related to the 2 atoms in the unit cell. So you basically also have these 2 points in K space that are relevant for your band structure. And what I will try to show you is that this very simple physics that originates basically from geometry in real space has fantastic consequences for qubits, if you want. Okay, so let's start out with graphene. Linear dispersion, let's just focus on the K point. And now you want to build a transistor. And you realize wherever you put your Fermi level in this band structure here, there's a finite density of states. There is one particular point, which is at the Dirac point, where presumably the density of states goes to 0, but obviously in reality it's not 0 because of interaction effects and all kinds of disorder. So you can never basically switch off this transistor because there's no band gap. So graphene is a bad material to start with to build something that confines electrons. So what do? You have no gap, no dot, no qubit. So you go to bilayer graphene. And bilayer graphene, these are just 2 layers of graphene on top of each other. And 2 layers of graphene on top of each other. It looks similar to dispersion. It's not quite the same because close to zero energy, you have a parabolic dispersion. It's not linear anymore, it's parabolic. And you have various bands because you have the two layers. And you can break the symmetry by applying a vertical electric field across these two layers. And then you see you open a band gap between these two layers. And a band gap is something that you fundamentally need if you want to confine carriers in a solid state system. Okay, now if you blow this up a little bit, you see that the originally parabolic dispersion is no longer fully parabolic. You have a band gap which is order of magnitude 50 milli-electron volts. So that's a small number if you compare to silicon and germanium and gallium arsenide. But if you work with millikelvin temperatures in a dilution refrigerator, then this is a huge energy scale. And for all practical purposes, it's a reasonable band gap. And it's interesting that you can tune it with electric fields. It's a tunable band gap. And if you look in more details, you see that you actually get this Mexican hat dispersion. And this Mexican hat dispersion has a lot of interesting features. It's topology in K-space. And this topology is actually, again, something which is tunable by an electric field. So everything that you do in graphene can be tuned by electric field. The band structure, the details of the band structure, the band gap, and many more things, as I will explain as we go along. Okay, let me walk you through our technology. Our technology is sticky tape technology to this day. So we have very dedicated PhD students with sticky tape. Our sticky tape is blue, and then we exfoliate one layer after the other. And it's very hard work. The yield is very low, and I think this is one of the fundamental limitations of that field. How can this ever be upscaled? But that's another question. So we start out with a layer of graphite. Then we cover this with hexagonal boron nitride, another one of these 2D materials that you can stack. Then you put a piece of bilayer graphene on top, next hexagonal boron nitride. Then you etch down a little bit, and you make these ohmic contacts to this layer of bilayer graphene, and then you put a top gate in the center. And now you see if you apply a voltage between the top gate and this back gate, then locally you create your electric field, and locally you can make a large band gap. And because you have two gate voltages, these are 2 degrees of freedom, so together they give you the size of the band gap, and they give you the position of the Fermi level in the band gap. So if you make a large band gap and the Fermi level is in the gap, then the resistance between source and drain should be infinite. It's like a switched off transistor. Actually, that's straightforward. The discovery of the band gap is now 15 years ago, but it took a long time to actually make a functional band gap that you can have an infinite resistance. Okay, let me mention here the hexagonal boron nitride. It's, I think, very underappreciated. These are the two Japanese gentlemen that supplied this to the entire 2D materials world. I think without them, our field wouldn't exist. I recommend you to check the citation indices of these gentlemen. It's absolutely stunning. So this is the schematic of how we build a device. I left out all the insulating layers. These are just the conducting ones. So there's a graphite backgate. Then this is our piece of bilayer graphene. Then you see the green gates. The green gates we call the split gates. And now when we apply appropriate voltages between the split gates and the backgate, then these regions here are insulating in bilayer graphene, and the current between the contacts has to flow through this narrow channel. And then there's a next level of gates. These are the blue finger gates. And now you can locally change the chemical potential in the channel between one of those finger gates. Okay, so let's look at the sample. Here are the contacts left and right. Here's our narrow channel. Here are our split gates. We don't touch them anymore. The back gate, we don't touch them because we have adjusted them that we have insulating regions. And the only thing that we tune is this little finger gate here in the center. So if this finger gate is unbiased, we measure some conductance along the channel, and you see schematically the band structure on the bottom. In this case, we talk about holes. So you see the Fermi level is at the top of the valence band in the source, in the drain, and in the channel. Now we can tune the position of the Fermi level below the red gate, and we can tune it to a regime where it's in the gap. And you see the conductance goes to 0. We have fully depleted the channel, so that's a transistor that you can switch off. And now you keep going, and in the center, what you start doing is you start populating the conduction band. And you see very, very nice Coulomb resonances showing up. basically meaning that you have created an island now. This island contains individual charge carriers, electrons in this case. They are connected to hole-type leads. So the confinement is done by lateral p-n junctions. So as you go along this channel here, you go from a p-type contact to an n-type island and to a p-type contact. And you see very nicely already here that they have peculiar features. So we can fill in electron 1, 2, 3, 4, 5, 6, 8, and so forth. And all of this is completely defined by gate voltages. Now what you can do is you can, of course, invert all of those gate voltages. And in the very same sample, you can fill in holes. And now you have 1, 2, 3, 4 holes and so forth on the other side. And you can actually build a device that has two dots, one containing electrons and the other one holes. That's something you cannot do in any other semiconductor. But you can do it here because the band gap itself is just a little larger than all the other energy scales in the system. Okay, now let's have a closer look at how we fill in electrons in the system. And I show you here a series of conductance resonances. The gate voltage here is just the voltage on the center gate, and you can think of it as being proportional to the energy scale in your zero-dimensional system. So that the energy difference between neighboring peaks, that's basically the energy it costs you to add an additional electron to your system. On the bottom plot, I'm showing you the difference between neighboring peaks, and you see we have to pay a lot of energy for electron number 4, for electron number 12, and for electron number 24. So this is what I would call Hund's rules for a graphene quantum dot. If you go back to the periodic table, it's easy to fill in the first electron, the second electron goes into helium, and then electron number 3 goes into the next shell, right? So you have to pay a lot of energy, and that would be lithium for the periodic table. Now what happens here, so it takes a lot of energy for electron going from electron number 4 to 5. So what is happening here, if you think of silicon, germanium, gallium arsenide, and so forth, if you have a small island, the ground state is something like an S-like state. Now this S-like state is twofold degenerate generally because of spin degeneracy. But now what happens in graphene is you have this additional degree of freedom, the valley degree of freedom. I told you there's the K and the K prime point in K space. That gives you an additional degeneracy, and you can read it off here directly. So the first 4 electrons, that's 2 for spin and 2 for valley. So I think it's very suggestive that because of this very simple geometric assessment in real space that we started out with, you can directly see that in the shell filling of a graphene quantum dot. So that's the S state, filled by 4 electrons because you have degeneracy of spin and degeneracy of valley. Now let's move on. Electron 4 to 12, the next 8 electrons. Well, what's happening? The next orbital state is a p state. The p state in 2 dimensions is twofold degenerate. So you have 2 for p, 2 for valley, 2 for spin. That's 2 to the power of 3. That gives you 8. That means filling in 8 electrons here. So we understand this one. Now let's look at this guy here. That's 12. So now we need some factor of 3 somewhere. Where does the factor of 3 come from? Now I showed you this Dirac cone, right? And this Dirac cone, we call it a cone because we think it's circular and symmetric, but it is not, right? In real life, in the real band structure, we need to satisfy this hexagonal geometry. So this cone, actually, as you go to higher energy, it starts having this underlying geometry of the hexagonal lattice. And we call that trigonal warping. So basically this cone is not just a circle, but it actually has a threefold geometry. And this is something that happens at very high energies, and usually you neglect that. But because we apply very large electric fields in our system in order to open a band gap, we are pushing these high energy features down to lower energy. And that basically means that we get 3 pockets in K space because of that trigonal warping. So what's happening here is there's a factor of 3 for trigonal warping, plus 2 for spin, plus 2 for valley. That gives you the additional factor of 12. So you see that all of the basic features of the graphene band structure, they show up here. Now let's see how we fill these states. So what I show you here is again the gate voltage axis. That's energy in our system. That's conductance, the color plot. And the vertical axis is an in-plane magnetic field. So it's a magnetic field that's oriented in the plane of the graphene. So it only couples to degrees of freedom that couple to in-plane fields. All the orbital degrees of freedom, and K prime are orbital degrees of freedom, they don't couple to an in-plane magnetic field. So it's only the spin that is left. So now what you can see is you see the first two Coulomb resonances, electron 1 and 2, they move to the left. They go down in energy as you apply a magnetic field. The next two, they go up. Okay, so now we know how we fill in the first 4 electrons in our S shell. The first 2 electrons come with the same spin, but with opposite K and K prime. And then the next 2 come with the down spin and also K and K prime. So that's already kind of an interesting situation. Look at the 2 electron state. The 2 electron ground state has 2 spins that point in the same direction. So I don't know any other system where that is the case. Look at the helium atom, right? The ground state, the 2 electron ground state is a spin singlet. The 2 electrons have opposite spins. If you think, for example, about the hydrogen atom, also 2 electrons, ground state is a spin singlet state. If you think about the same thing in gallium arsenide or silicon, the ground state for 2 electrons is always a spin singlet. Here, the ground state is a spin triplet. Okay, now if you start thinking about qubits, that's really bad news, right? If your ground state is a triplet, what will your qubit ever look like? Now, let's move on. That's the first 4 electrons. This is the next 8. And you see for the next 8, it looks the same. The first 4, they move to the left, lower energy. They come in with the same spin, like Hund's rule in the periodic table. And then the next 4 here, they come with the opposite spin. So if you plot these slopes here in terms of a G factor, you see that's the first 4 electrons, spin down, spin up, the next 8 electrons, and then you see it gets a bit more complicated because obviously our single particle model that I've used so far doesn't hold anymore if you have 12 electrons or something like that in your quantum dot. But overall, you can see and understand how this spectrum looks like in graphene, and it has an interesting twist to what we know in other systems. And that twist basically comes from the valley degree of freedom, which doesn't exist in other materials. Okay, now let's try to measure the lifetime of these states, right? So far I've showed you ground states of various electron occupations, but now you would like to build something and you want to understand how long does a state actually live. So what you see here is a more complicated schematic. So the green gates, they're our old split gates, and these green gates are used so that you have no carriers below and a gapped region. So you're left with the 2 white channels here where the current can flow. Now the top channel, this is where you build your quantum dot as before, and the bottom channel, you can also build a quantum dot or a constriction or whatever, but it works as a charge sensor to what's happening on the other side. This idea of having a charge sensor, it has been done in gallium arsenide, silicon, germanium, and so forth, and it's the same thing here. You basically have 2 quantum devices. One is the quantum device that you would like to understand. The other one is a quantum device that is capacitively coupled, and its transmission, electrical transmission, depends on the occupation of the dot on the other side. So you basically can measure how many carriers are here on the upper channel while monitoring the charge current on the lower channel. So without really passing a current through the quantum dot itself, you monitor what's going on in the lower channel. And here's an image here of the real device. So now we do something called the Elserman readout. The Elserman readout is one of those fundamental experiments, early development in gallium arsenide by a PhD student, Elserman, in Delft. And that basically is an easy experiment to measure lifetimes. What you do is the following. You take your quantum dot and you apply a small magnetic field that your ground state is Zeeman split. And then what you do is you have a load phase, and in the load phase you put these 2 Zeeman split states between the Fermi levels of source and drain. So in the load phase an electron can come in, and the electron can come in into the upper state or into the lower state. Then you go to the read state. If your electron was in the ground state, it stays in the ground state because the ground state is below the Fermi levels in source and drain and it cannot get out. If it was in the upper state, it can leave to source and drain and is replaced by another electron with the opposite spin in the ground state. So if you have loaded the electron in the ground state, it just stays in the ground state. If you load it in the upper state, you can see the electron leave and come back, and that tells you something about the lifetime. And then, of course, you unload and you start from scratch. So let me show you some typical experimental data. That's the detector signal. That's the waiting time. So here we load, and then the important thing is here the read phase. And you see in the read phase, the detector shows, aha, electron left, and electron came back. That's the situation where you have loaded the excited state, electron left, and came back again. This is another experimental result where you have apparently loaded into the ground state, the electron stays there, your detector sees nothing. So you can take this one here, and you can measure it many, many times. You introduce statistics with that, and you get out a lifetime. So, and this is what we call basically the blips and the amount of blips as a function of the load time. So if the load time is 0, you never load an electron in your system and you never see a blip. If your load time gets very long, independent on in which state you have measured your electron, it has time to relax to the ground state and you see no blips. But at a specific load time, which is comparable to the decay time of this quantum state, you get the maximum number of blips. And you know these exponentials, you can fit them, and we find that if you go from the excited state to the ground state, it takes about 20 milliseconds to relax. That's pretty good. That's on par with the best measurements in silicon. So these are pretty good T1 lifetimes of quantum states in graphene. Now, let's think a little bit more about this energy spectrum, because it's really very different to what we are usually used to. I told you that the ground state...
All of these things, details depend on your sizes and the way you've made them, right? I mean, every time it's slightly different. It's not like an atom that always is the same.
We are not as good as atoms. For sure, not every device is different. Actually, taking the same device, cooling it down again, leads to a rearrangement of the impurity configuration. But we have, so this, it's not 20 milliseconds, it's 15 to 50 or something like that. We have measured many devices, they're all in the same ballpark, but it's not a unique number here. Yes, absolutely. So let's lean back and think about the energy spectrum. I told you that the ground state is fourfold degenerate in graphene. Fourfold, 2 for spin, 2 for valley. Well, actually, spin-orbit interaction in graphene is not 0, right? It's very tiny, but it's not 0. And there have been all kinds of numbers in the literature, but meanwhile, there are different experiments with different groups that basically tell you that the spin-orbit interaction is 75 microelectron volts for graphene. For bare graphene, bilayer graphene, 70 to 80 microelectron volts. So that sounds like a small energy scale, but it's a significant energy scale if you work at 10 millikelvin electron temperature. So basically, this is much larger than KT. So what happens is that our fourfold degeneracy is actually lifted in 2 doublets. Our quadruplet has been split into 2 doublets by the intrinsic spin-orbit interaction in graphene. And each of these doublets, you see they are funny doublets. Let's look at the ground doublet here. You see the blue curve and the violet curve, they have opposite spin and they have opposite K. It's very similar to TMDCs, where this is called spin-valley locking. And the upper state has the same thing. Now what happens if you apply a perpendicular magnetic field? A perpendicular magnetic field couples to the spin, but it also couples to the orbital motion of the electrons. And the K's and the K primes, they're orbital quantum numbers. And actually what happens is, because of the Berry curvature in K space that's related to these topological properties, the orbital magnetic moment that you find for these electrons leads to a linear shift in magnetic field. So we call this the orbital or the valley-Zeeman effect. And the valley-Zeeman G factor can be anything between 20 and 200, depending on the gate voltages that you apply. So it's not given just by graphene, it's given by the band structure and by your electric fields in your system. So you see this valley-Zeeman effect. And of course, you also have the standard spin-Zeeman effect. And you see that's the reason why, for example, the lower doublet splits more, because it splits by valley G factor plus spin G factor. And the upper one splits by valley G factor minus spin G factor. In this particular case, the valley G factor is around 20. The spin G factor is 2. So it's 20 plus 2 and 20 minus 2. It's also interesting what happens if you apply an in-plane magnetic field. Then you don't couple to orbital motion. You don't lift the degeneracy, but you start aligning the spins in the two states in the direction of the magnetic field. Now, if you look, I didn't tell you that in my last experiment, what a relaxation mechanism plays a role, then you see, let's assume we work here. We go to a small magnetic field. We have the Zeeman split state. We want to go up here to down here. Then you see you have to flip valley and spin. The experiment that I've shown you before was done at higher magnetic fields. It was done here. And there you see the green state decays into the violet state, which is the same K, and you flip the spin. So the time scale that I've showed you was a pure spin flip, not a valley flip, right? Now you wonder, and now you see you can flip the spin, you can flip the valley, you can flip the spin or the valley, or you can flip the spin and the valley. So it's much richer than the qubits in the other material systems. So let's now go to the regime where we flip spin and valley. So here are all kinds of lifetimes. This is the spin lifetime. This is spin or valley lifetime. This is the most important one. This is close to zero magnetic field where you have to flip spin and valley, and it's 38 seconds. Actually, meanwhile, they live so long that we can't measure it anymore. So what we have found is that it is super hard to flip the valley. Actually, now you have a qubit with an infinite lifetime. So from one point of view, this is the best thing you can have. But from another point of view, that's very bad, because then how do you manipulate your qubit if your spin lives forever, right? But from a physics point of view, it's very interesting. And of course, in the experiment, it's always easy to get the time scales lower, right? It's harder to make them longer. So what's happening here? Well, let's think of the simplest possible qubit that you can have in a solid state system, which is a charged qubit. A charged qubit is a charge here or there, or a superposition of both of those states. So the charge moving back and forth, that's an electric dipole moment. An electric dipole moment couples to a fluctuating electromagnetic field. And we know that all solid-state systems are full of two-level fluctuators that create fluctuating electric fields. And that's the reason why the coherence time of charged qubits is lousy in all kinds of systems. It's nanoseconds or something like that. So that's why a charged qubit will never make it. Now, what is a spin qubit? A spin qubit is spin up or spin down. So that's a magnetic dipole moment. Magnetic dipole coupling is much weaker. Also, we have fewer fluctuating magnetic fields in our systems, and that's the reason why the spin qubits are better, much better than the charged qubits. Now think of the valley qubit. What is the valley qubit? Well, the valley qubit is you're at K or K prime in K space. You are at the same position in real space, you have the same spin, you don't couple to electric and magnetic fields. So you have to go a huge distance in K space. It's the size of the Brillouin zone. How do you get from K to K prime? Well, you need a very short-range scattering event. You need an atomic defect. If you don't have an atomic defect in your system, you don't make it from K to K prime. Well, graphene is an almost perfect system. It has, at least for these systems, no atomic defect. And that's why it's so hard to get from K to K prime. And that's why these qubits have this very, very long lifetime. And now we call them, to give them a general name, it's a Kramers qubit, because it's not a valley qubit, it's not a spin qubit. These are just two states that have opposite valley and spin quantum numbers, and that's why their lifetime is so long. So that's, in some sense, a quite unexpected outcome, but it's a very nice outcome, because it tells you, and again, it's funny, it goes back to this primitive unit cell in real space that has two atoms. It ends up with a very nice qubit with a very, very long lifetime. Okay, so that's our motto. quantum dots in graphene are just fantastic. But now let's move on. Let's think a little bit more about the spin-orbit interaction. Spin-orbit interaction is something intrinsic to, I think, to any atom that we have, sometimes stronger, sometimes weaker, and it has good and bad features. It has, if you want, bad features, as I said before, because it gives rise to spin-valley coupling, spin-orbit coupling, spin-charge coupling, and that gives rise to decoherence. At the same time, it's a good method to tune your spins, because you can tune the charge with electric fields, with gates, and via spin-orbit coupling, you can use gate tuning to influence the spin. So it has all of these different features. So I showed you here the band structure. This is ungated bilayer graphene, 2 parabolas. You open a band gap by applying electric field. Now there's another class of materials, the so-called transition metal dichalcogenides. These are all materials that you can exfoliate like graphene. Unfortunately, they are not very clean, so the electron mobility is not very good. And they have extremely strong spin-orbit interaction. It's like half an electron volt. It's a significant part of the band structure. So it's completely on the other side of graphene. So what you can do is you can place a piece of transition metal dichalcogenide. Actually, it doesn't matter what you take, whether it's tungsten diselenide or molybdenum disulfide. They all act about the same way. It behaves like an insulator, and this insulator injects spin orbits in the action in a similar way as a superconductor injects superconductivity in a neighbor. We call it proximitized spin-orbit interaction. So, and it has a very short decay. So in other words, you see the band structure here. You see the upper band has split now because of the presence of this TMD next to the graphene. And now, because of your gate voltages, you can park your electrons in the graphene layer next to the TMD or away from the TMD. If they are away from the TMD, they don't feel the TMD anymore. And so just by moving your electrons by gate voltages by one layer, you switch on from strong spin-orbit interactions to weak spin-orbit interactions.
You know, within the microscopic description, what is happening? How do you turn off and on the spin-orbit coupling?
So there are DFT calculations that have shown that it's basically the molybdenum atoms. They are in molybdenum disulfide, they are the heavy atoms. They are responsible for the strong spin-orbit interaction in the TMDs. And these orbitals penetrate into the graphene. I mean, it's an exponential decay into the neighboring layer. And that gives rise to the proximitized spin-orbit interaction in this material system. So there are calculations that show this. So
for example, for a single atom, it's just, you know, you can consider rotation of the electron about the nucleus, and then you have the magnetic field and the coupling. So here, do you have some intuitive, simple explanation?
Well, I think in a solid state system that's built up of atoms, on the atomic scale, spin-orbit interactions works like you just described it.
Then I don't understand how you can turn this off.
By going away from it, because it decays exponentially to the outside of the material. It's a function of distance. It's contained in the wave function of the electrons, and this wave function, if you're close by, so you have a material of TMD that has wave functions in the conduction and valence band. The wave functions contain spin-orbit interactions. You have your graphene next door. If these wave functions start overlapping, then there's a coupling between them. If they cannot overlap, then there's no coupling. It's a matter of distance. Yeah. So here I show you a quantum point contact. So this is quantized conductance in a 1D channel. And this has been done in gallium arsenide 35 years ago. And you see that's graphene, nothing special here. You see quantized conductance in units of 4 e squared over h. That's what we expect. Again, factor of 4, 2 for spin, 2 for valley. Now you make the same experiment, but you put a layer of tungsten diselenide on top. And now what you see is there are additional plateaus at 2, 6, 10, and so forth. So you have lifted this 4-fold degeneracy by the additional spin-orbit interaction. Okay, so you can just look at it and you see there's spin-orbit interaction or you should say I've lifted the fourfold degeneracy by putting this additional layer there. Now you can look at this differential conductance as a function of magnetic field. You see, every time you have a plateau, you get one of these states here. Each of these states splits linearly in magnetic field. That's because of this valley-singlet effect that I explained to you before. I used to see how they cross and they evolve into the quantum Hall regime. Now you do the same thing on a layer, bilayer graphene with tungsten diselenide. You see each of those states has split into two, and those two states move parallel. They each split up in magnetic field, then they move parallel in magnetic field. So this scale I told you is a gate voltage. The gate voltage can be converted to energy. So that's an energy scale. So you can already read off the distance from here to there. That's the energy scale between the ground state of the confined system to the first excited state. Similarly, I can say on the right-hand side, the energy separation between here and here, it's simply the spin-orbit interaction. And that's already an interesting result, because usually spin-orbit interaction is hard to measure, right? You have to do some weak anti-localization measurement or something like that, yeah.
What tells me that is not screening here? Just the standard screening that we use in condensed matter.
So what?
Because I would find more intuitive to think about the screening of the due to the presence of the TMD rather than this proximity spin orbit. So what is the fingerprint of spin orbit?
Mm-hmm. So when you say screening, you need free carriers, right?
Yes.
The TMD is an insulator.
Yes, but you will screen at high frequency, but okay.
Yeah, this is DC. Yeah. So
So you say screening is out?
I think screening is out, but I agree with you. I haven't proven to you that it's spin-orbit interaction. I've showed you that I lifted the degeneracy. Okay. Whether that's spin-orbit interaction, we have to find out. Yeah. But it turns out that all of these TMDs in this range are perfect dielectric insulators. Okay. Okay, so you can now build a quantum dot. I showed you a TMD. You can build a quantum dot as I've shown you before. You take this quantum dot, that's the part of a Coulomb diamond. You can measure the excited state, and you see that you can measure for weak and for strong spin-orbit interaction. And you see here, you can directly read off how far this goes. It's 0.2 milli-electron volts, and here it is 1.5 milli-electron volts. So we build a quantum dot in the graphene layer away from the TMD, then we have weak spin-orbit interaction, and just by using our gate voltages, we use exactly the same sample in the same area with the same size, and we build a quantum dot in the graphene layer next to the TMD, and we get this much enhanced spin-orbit, I should say, lifted degeneracy, right? Okay. So, and now you can make many quantum dots, and you can do a lot of QPCs, and you can, we call it spin-orbit interaction, the splitting here, as a function of the electric field that you apply, and you see you can tune it from 1.5 millivolts. Let me put that in perspective. The bare spin-orbit interaction in graphene, as I said, is down here. It's about 100 microelectron volt. So you have gone up by a factor of 15. If you compare it to the TMD, the spin-orbit was 500 milli-electron volts. So you have come down a factor of 500 from the TMD, and that's the exponential tail of the wave function that penetrates into the graphene. Okay. And now you have a parameter that you can tune. I think that's something very new, that spin-orbit interaction is not simply a parameter in your system, but you can tune it over orders of magnitude. And yeah, now you can ask yourself, what happens to the lifetime, right? I showed you lifetimes for this system. Here we had the intrinsic spin-orbit interaction, about 80 microelectron volts. Now I told you we can raise that to about 1.5 millivolts. So the energy spectrum without TMD looks like that. With TMD, it looks like that. So now we measure the time it takes to decay here and the time it decays to decay here. So does the spin-orbit interaction do anything to your spin valley qubit? And I show you the results directly. That's the same. That's the Ensslin readout that we are using. And we come directly to the results. So this is the energy spectrum, weak spin-orbit interaction. If we look here, that's our Kramers qubit which means we have to flip spin and valley. Here we only flip spin, here we flip the valley. And you see we go from our 1 second or something like that over here, long lifetimes, to much lower lifetimes on the other side. Now we take a sample that has transition metal dichalcogenide on top. You see we have this huge spin-orbit induced gap, and you see what we find. We find lifetimes that are so long that we can't measure them anymore. And the reason for that is because you have put all the excited states so far away. Decaying from one state to another state always involves virtual transitions to higher states. If the higher states are far away, then actually they don't give rise to this decay anymore. So this is as high as we can get. You can imagine if you have 100 seconds lifetime and you need to take 1,000 data points to get good statistics, then it goes beyond the lifetime of a PhD student to get reasonable statistics. So I think the lifetimes are as long as you can measure them. And that's very different to other qubits that we have in our systems. So if you go to silicon or germanium, spin orbit is always a nuisance. It shortens your lifetime. Here it increases your lifetime. Okay. So now let me switch gears a little bit. I hope I convinced you that the graphene qubits are the qubits of the future. Still lots of steps missing, of course. Not talking about many of those with our sticky tape technology. But I want to give you a few other aspects of these systems that I think are pretty unique. So you know that you can twist graphene layers. It's also a bilayer system. And you can see superconductivity. And what we have done is we have taken such a system and we built a Josephson junction. And this is well known for standard systems, taking aluminum oxide, and so forth. But we can do the same thing by gating. So here's our twisted magic angle graphene. We have gates here. We can induce superconductivity in the leads, and then we have a center gate to create an insulating barrier, because you can switch between superconductivity and not just simply by gate voltages. And if you do that, you find a very nice Josephson junction behavior. You can apply high frequencies, and you see very nice Shapiro steps. So if you look in the textbooks, this looks very similar to what has been done in aluminum and aluminum oxide. So you could also argue it's another justification that we call this a superconductor. You can go further than that. You can drill a little hole in your sample, put two barriers out there. You see you enclose a hole here. You can build a squid, and you find magnetic field periodic oscillations in the squid. So each time you have magnetic flux penetrating your loop, you're changing the phase of your loop by 2 pi, and you can calculate from the distance between these peaks here what the charge is, and it's 2e. So we can actually show that this is a pretty standard superconductor that allows you to build Josephson junctions and SQUIDs. You can also do something else. You can now go back to quantum dots. So this is basically a piece of bilayer graphene, superconducting. You see our gates here. And now what we can do is we can basically make the outer graphene superconducting and make one of those gates, put a voltage on it, that it's just a standard semiconductor island. And then what you see is, this is, let's look at the bottom here, zero magnetic field. That's a gate voltage applied to one of those gates. You see periodic oscillations. So this is a Cooper pair island. This is basically a superconducting quantum dot where the leads proximitize the dot. And as you apply a magnetic field, you kill superconductivity. You see that each of those peaks splits into two. And up here we have standard electrons tunneling through your system. So now you see you can actually play with the superconductivity in your quantum dot. It's yet another degree of freedom that is available in graphene. And you can put them in different regimes. You can imagine you can make the lead superconducting, the dot normal conducting, or the other way around. So there's a huge playground of things that you can deal with, and it's a monolithic device. It's a single crystal. It's not like in other systems where you have to put a superconductor on a semiconductor. You worry about the interface, about impurities at the interface, and so forth. This is all done completely gate controlled. Okay, so that brings me to the end, and I like to dream a little bit about at the end. So we can build Josephson junctions, quantum dots. I didn't talk much about topology, but it's also one of those parameters that's tunable by gate voltages. I think the valley degree of freedom is really fantastic because it changes our energy spectrum. The qubits that I hope we will have at some time in the future will be a very different qubit from the other qubits in silicon and germanium. Spin orbit is yet a new ingredient that you can tune by gate voltages. You could even think further. There are 2D materials that are ferromagnetic. You can use them on the other side of your stack, and you could switch on and off ferromagnetism in your system. We haven't done that, but I think it's doable. And so all of the parameters, if you think of solid-state physics, you have them at your hands, and you can tune them by gate voltages. And you can make, from the physics point of view, very interesting hybrid quantum systems, very difficult to do in other systems, other materials. And as I said, the valid degree of freedom with the long lifetimes is very promising for qubits. So thank you for your attention, and I thank my group for the work.
Thanks, Klaus, for this beautifully presented talk on very interesting textbook-like results that even a non-expert can follow. There are probably questions. I have a few, but I'll let you go first. Who wants to? All right, I do go first. So this really looks beautiful, kind of like a lecture that you would give and tell people how to design artificial atoms the way quantum dots were presented many, many years ago, how you can control everything electrically and all of that. Can you tell us a little bit about the dirt?
The dirt.
I mean, you had the dreams. I think we all want to dream. But what is preventing, or what are the prospects really of this type of technology, which I think makes a lot of sense in comparison to other contenders to quantum computers and all of that?
So maybe I was too optimistic, right? There are many, many barriers that we yet have to overcome to get there. Maybe talking about impurities, for example, or lattice imperfections in graphene. Obviously, graphene is not perfect. I mean, very often you have a sample in the lab and then you say, oh, it doesn't work, let's measure the next one. I think these are the samples that have an impurity. We simply don't see nice Coulomb blockade, we don't understand what's going on, and so we move on to the next one. And I think our selection process leads to samples that have no atomic defects. And it's known from STM studies that there can be micron-size areas without any defect. So in that sense, it's completely compatible with that. But obviously, if you make 1 billion of that, transistors, you will end up with a few of them that will have a defect. So that plays a role. And then, of course, our sticky tape technology, you know, our samples are getting ever more complicated. Life is getting harder for our PhD students. And there are limits to that.
That's a place usually that, you know, you bring industry and they solve your sticky tape problem by throwing in a whole bunch of money on it and somehow brute force technology that makes it work. So let's leave that aside. But I think things like defects, those are more fundamental material science issues that industry can't always get rid of either. So how serious is that? I mean, in optics, we have issues with things like spectral diffusion and things that have to do with, I say, the floppiness of any crystal or any material. So when you talk about graphene, you actually mentioned this is a perfect crystal, and now you're saying that it does have defects. So how serious is that problem?
So let me maybe start with the insulator, right? The hexagonal boron nitride. As I said, every solid-state system has two-level fluctuators. All of the oxides that are used these days, be it for silicon dioxide transistors or for the superconducting qubits, they are all based on amorphous oxides. What we have is crystalline hexagonal boron nitride, which I think is intrinsically better than any amorphous oxide that you can make. And so I would even argue that this hexagonal boron nitride, if it were available wafer scale, it's the best insulator that we have in this world at this point. It has defects, and the people are doing optic studies, and they find all kinds of interesting single photon effects in it. So it's not defect-free, but it's better, I'm pretty sure, than most of the silicon oxides that we have in electronics and aluminum oxides that we have in superconducting electronics. So defects will play a role, but I think they will play a role like in any other solid-state system. And from the noise levels that we have so far, we are at least competitive with what exists, if not better.
Other questions? Yeah, Alexei.
I have a question. Does string theory play a role in science, or is it totally different?
Go ahead.
So continuing maybe a bit along the same line, so you showed very nice results for the lifetime, and what about the coherence time? Have you measured that?
So we are on it. We have no number yet. And that's, of course, the crucial time.
What would you expect? So do you expect like nanoseconds, seconds?
So we have done a bet in our group. It's on the blackboard in the group room where everybody puts down a number. It varies between a microsecond and 100 seconds. So I think everything is possible. There are critical people that say at the end of the day it's a solid state system. So you will end up in the best case with a millisecond. But you could also argue graphene is cleaner, 2D materials are thinner. So it also actually screening of the metal gates, you could also argue helps because they are closer by. And that reduces any kind of two-level fluctuation. At the end, it's all charge noise in the problem. And the question is, how relevant is the charge noise in our systems? So I don't know.
So there's, can you pass on the microphone while you're doing that? So can you say something also about the how difficult it is for your electronics? I mean, how good of electronics do you have to not add instrumental noise to your measurements? Yeah.
So we have optimized our electronics back in the days for gallium arsenide quantum dots, measuring them at 5 millikelvin and so forth. And you need very good electronics, but what we are measuring today is not as sophisticated as what we did 10 years ago. So measuring Coulomb blockade in these systems, I think this could be done in many labs around the world. You need very good shielding of your wires, you need to know your amplifiers, but there is no secret behind that. Many people could do that.
Okay.
You showed at some point that there is this hole that you drilled inside the graphene. So can you explain how you make that and what happens to that atom? Like, is it connected to something?
You mean how we etch away the...
Yes, the edged part, exactly. So at the edge, you'll still have these carbons which are probably bound into something, right?
So you're worried about the etched edge, the carbon...
The edge itself and how you make it, actually.
So what we do is we basically take the twisted graphene, encapsulate it in boron nitride, and then we do a dry etch that goes through the top boron nitride layer and the twisted graphene layer below. And you're absolutely right that then you're left with an etched edge of the graphene, which has dangling bonds, which is terrible, which you avoid with all the electrostatics, right? Which you don't avoid once you start etching. And this particular device was relatively large, so the orbit was a micron. So the wave function saw very little of the edge. But if you build a quantum dot that way, it wouldn't work because it's just surrounded by dangling bonds of the graphene, and then the beauty of graphene is gone. Yeah, thanks.
One last question.
Okay, so there was also, like, when you're loading your electrons in this small region, so I assume that the electron is actually very localized, right? And do you have like is there like a wave function that you can assign to this? And what would be the difference between the wave function of k and k prime point?
So you're talking about the electronic wave function in real space in the quantum dot.
Yes, yeah, exactly. Like that p orbital that we have as an image, for example, what would be the difference between these two, the first two electrons that you're feeling, K and K prime?
So I cannot give you a precise number, but from the Coulomb charging energy, you can calculate what is the size of your quantum dot. And we know that the extent of our electronic wave function is around 20 nanometers. And obviously the P state will be more extended than the S state, but I can give you a rough estimate, but I cannot measure it.
So maybe I ask one final question. I know that at different times, or at least at one point, you played with the idea of shining light at your quantum dots. I think that was still your gallium arsenide quantum dots, probably. So can you tell us about the potential of using photons in conjunction with your dots?
Yeah, thank you, Wade. That's a very nice question. So, you know, that was my dream a long time ago when you were there and with Attach and so forth. And it turned out that all the quantum dots either were good for optics or were good for transport. They were never good for both. However, and I think graphene will never be good for optics because the band gap is too small. But you can also build these quantum dots out of transition metal dichalcogenides. And they are very good for optics, and they are very good. They are not very good for transport yet because they have a lot of impurities. The mean free path is short. Nobody knows how to control individual electrons. But there is one fundamental advantage of these 2D materials, which is obvious, but I think nobody has exploited yet. You know, they're thin as it gets. So you can build a perfect insulator of this hexagonal boron nitride that is 3 monolayers. 3 monolayers is enough to have an insulator. That's a nanometer. So let's assume you make 1 monolayer TMD encapsulated by 3 nanometers of insulator. You could make gates around it that are 2 nanometers. If you could make a quantum dot that is 1 nanometer. That would be fabulous for optics and for transport. The problem is nobody can make these gate electrodes with that accuracy. So I think we are no longer limited by materials. We are actually limited by so if there's a smart person that has a scanning probe technology that can make that, I think there's a fantastic opportunity for these 2D materials. I think that I'm still hopeful that this works at some point.